Today's submicrogrids, something like our campus, something like your campus, small communities. There are various types of sources, renewable sources and non-renewable sources that are connected to the grid, and then they need to interact harmoniously. So let us have a look at PV and the sub-microgrid interaction along with many other sources that are linked into the grid. Now what is a sub-microgrid? Now if you take a sub-microgrid, which could be a large building, a large community, a large campus, schools, colleges, they all can be examples of sub-microgrids. There is one important port in the sub-microgrid, the source port. Ports from where power is drawn, input to the sub-microgrid. There is the sink port. Loads are connected, various different loads are connected to the sub-microgrid, and that is another important port. And then you can also have bidirectional ports like the battery, where under some condition it is pumping energy into the grid, and under some conditions drawing energy from the grid for charging. There could be many source ports, and there could be many sink ports. And the sources and the sinks can be from different energy domains. So in a sub-microgrid, today's sub-microgrid, these are some of the challenges that you will see. There are different sources. Before, there was always a single source coming from the grid, well defined, that's it. But today, there can be a PV on the building, there can be a small hydel system, there could be a windmill on the roof, all this pumping energy into the grid. There is the regular mains grid also pumping energy into the grid, and then the various loads, batteries and UPSs, which sometimes give power, take power. All these are complex systems that are connected to the grid. So you have multiple sources and sinks, and sometimes in this case of the bidirectional ports, we don't even know which is a source, which is a sink. At a given point it can be a source, at a given point in time it can be a sink. So all these aspects, and still how to maintain the quality of the grid. Can the grid have a THD less than a particular value? And can it maintain the wave shape? Can we inject power into the grid at unity power factor? Can we draw power from the grid at unity power factor? And extensibility of this sub-microgrid. Can, if there is not much load requirement in my building, let us say a neighboring building needs load, can you transfer some amount of power from this building to the other building? These are extensibility issues that will come in. So the sub-microgrid is a growing area, also linked tightly with the smart grid area. Let us look at some of these issues, and we will take, in this case, the help of integrated magnetics for an example case. Consider this flux rate switch. It is a magnetic switch. Now let us see what it is and how does it work. Now consider a core in this fashion. So this is an EE core, two EE cores joined together, and let us say I have put some winding on this R, and likewise I am going to put some distributed winding like this across this. Now across this, let us connect the grid. So if I connect the grid, I am imposing a voltage, a fixed voltage. It's a voltage source across these terminals. So magnetically what is happening? So this is a magnetic equivalent circuit what I am trying to draw here. So inside in the magnetic core, magnetically there is a d phi by dt. So if the voltage is fixed into the magnetic domain, by the Faraday's law, V is equal to N d phi by dt, N being fixed, d phi by dt is directly linked to the voltage. So the voltage source on the electrical side. So it is like in the magnetic domain I have a d phi 1 by dt source. Now across these terminals I will connect the load, some load. So magnetically also it will look as though I have connected a load across here. So d phi 1 by dt, which is the flow, flows through this magnetic circuit, through this coil. It divides part in this fashion and part in this fashion. So accordingly there will be an induced EMF here and an induced EMF here, and together in the electrical domain they will add and impose on the load. Now I will introduce one more coil here on this arm. I will introduce another source here like this, which is going to provide d phi 2 by dt. So equivalently it will look like for this load it is having a voltage here proportional to d phi 2 by dt, another voltage proportional to d phi 1 by dt, and they both add up and then it is coming across this source. So that is what is happening here. Now let us say I include one more winding here. Can I include one more winding? Now here d phi 1 by dt is being decided by this voltage source. Here I cannot put another voltage source to decide another d phi 1 by dt because this is a single arm. The d phi 1 by dt can be decided by only one voltage source. This is reflected. So here I can place a current source and decide only the MMF Ni across this winding. So therefore a current source something like this in parallel can come. So this can have the same d phi 1 by dt, but it can decide the Ni that comes across this winding. So and thereby the amount of current that I inject here. So this should be like a current source. So this can be a voltage current source, a voltage controlled source. This has to be a current controlled source. So this gives us an idea of how we can use this magnetic element here. Now let us say I feed in more current, then here the voltage is fixed, the load is demanding power. This will provide MMF which will drive power into this load, and that much less can be taken from the grid. So both these units can supply power to the load. And then a third component here, a voltage control source, can also supply power to the load. So let us see how we can make use of this concept. So looking at this equivalent circuit and this voltage control source is affecting this series source component. So therefore I can say this is a series compensator. This will compensate the d phi 2 by dt, this series part, this series EMF. And this is a shunt compensator. This will come into effect on this component here, and therefore it can draw more current or give out more current, and therefore it can behave like this shunt compensator. Now let me take the case of just only the two sources. One is the series compensator, which is a voltage control source, and then there is this grid. Now for the moment, let us say the grid is switched off. So the grid is not there. And let me introduce one more winding into the central arm here. And I will put a switch there, direct one simple single pole, single throw switch. Now if you close the switch, the voltage across that is 0. V is equal to n d phi by dt. Therefore, the d phi by dt here has to be 0 because n is not 0. So once the d phi by dt is 0 here, it is as though this arm, core arm, has vanished, as though it has been switched off. So this is the concept of the flux rate switch. When I short circuit a winding here, the other winding should exist so that there will be transfer of MMF and d phi by dt to the other arms. There should be a path, just like inductance freewheeling. In that case, when you short this, d phi by dt for this arm becomes 0, and this is out of the picture now, as though it is only this whole core. Now the grid is not there. This will be supplying the entire d phi by dt in this single, similar to a UU type core. So this entire core, only the voltage equivalent d phi by dt corresponding to this voltage equivalent to be circulated, and as though the load is connected directly to this. So as though the grid portion is shorted. So under that condition, let us say grid has gone off, this source can power the load. So this is the entire integrated magnetic scheme, the basic principle. So I can have a current control source and the grid in one arm, and they can share power and put power to the load. Now suppose the grid goes off, then I will use this flux rate switch to remove this arm from the picture. Then the current control source and the voltage control source can together supply to the load. So in this way, you can make it operate like a UPS. When the grid is not there, these two will be supplying to the load. When the grid is there, this will act like a series compensator and make it look like a stabilizer, and the shunt compensator, the current control, can be made to look like a var compensator. This current control source can take up all the reactive part of the power, and the grid can give only the active part. So once the current control source takes away the reactive part, automatically only the active part is drawn from the grid. So you can see that you can do var compensation with this current control source. So these are the many uses that one can have in this kind of an integrated magnetics type of schematic. Now there is no limit to the number of current control sources that you can put here. You can put any number of current control sources here. So this will be like many multiple sources. Likewise, here also I can have any number of current control sources separately. There can be only one voltage control source, the remaining can be current control sources. That way one can accommodate in the same core the power being generated and transmitted from other renewable energies, other distributed energy resources too. Let us see how this can be used for applying for grid interaction. Now consider this integrated magnetic system, and I am going to place it here. There is a grid here, and I have a voltage control source and a current control source here, and there is a flux rate switch, and this is the load. And to this current controlled current controlled terminal. I have a PV module and the inverter, and the inverter output through an inductor. I am integrating it to this terminal. The control for the inverter is SPPWM. You measure the line currents, line voltages, DC link voltages, and then I can shift the AC to the DC. We know how to do the transformation. ABC to alpha beta to DQ, and then here we are in the DC control domain, just like we discussed earlier. And the synchronous angle estimation can be done from the line voltages. So I will have ISD, ISQ, VSD, VSQ, and you could do voltage control or current control. So if you have to do voltage control, you need to have two extra controllers, VS star or VSD ref. VSD is fed back, VSQ ref and VSQ fed back. I have ISD and ISQ, the current controlled by another set of PI controllers. All these possibilities. So you could do MPP, can do unity power factor by setting ISQ 0. You can also do harmonic cancellation, many such possibilities for each of these inverters. Maximum power point tracking, how do I introduce it? Let us say we take one of the algorithms. Remember the hill climbing algorithm where we had a P base and the current value of the P moving up. Similar algorithm. So you sense from the PV sense circuit, then you give the VP and IP, slow RC, fast RC to get the P base and the P current, the fast power and the slow power. Use it through the comparator. We know this block diagram, a toggle flip-flop, averaging circuit, comparing it with the carrier, and then drive to the switch to the inverter. So this is the normal thing. But what we can do, what we have been doing, we cut this portion and give this directly to the current reference. So you see that ISD, VSD and this MPPT algorithm will come in here. This is ISD star or ID star. And from this you know how to go back from DQ to ABC domain, DQ to alpha beta to ABC. This goes and powers up this inverter. So once the inverter output voltage is according to our reference, there is an inductor and then it interfaces at this point. So this will be the current injection. So current controlled injection to this winding. There is already voltage defined by the grid. Said we could also do series compensation. So we could have an inverter here and PI controller. You can measure from the output, and let us say we define a pure sine like this, and then we can take the feedback from the output here. So this series compensation operates in this way. Now let us say the grid is not the full 230 volt RMS, and then it is probably distorted too. Now d phi 1 by dt, this is d phi 1 by dt. This is the portion which is coming directly from the grid reflection. So you feed that here. So this is the distorted grid representation. This is what we want, total pure sine wave. So this minus this would be by how much the grid has to be repaired, or the difference by amount of which the grid has to be added in such a way that the voltage across the load will become pure sine wave. So this too, the subtraction of the pure sine and the distorted sine coming from the grid would be the difference makeup. That will become the reference here. So this voltage output here is actually coming from this inverter, the series compensator. This is d5 by d2 by dt. So this is being fed back here, and this will try to ultimately reach whatever this value is, which is actually the difference between the pure sine and the distorted sine coming from the grid. So this value here will actually be making up for the difference. So this difference, which is made up by this plus the distorted grid, will make the voltage across the load a pure sine wave. In this way, series compensation can be achieved. Observe here in the experimental result of this, the grid voltage is distorted, flat topped. So the distorted voltage is compared to the pure sine, and the difference between them is actually used for compensating here. And this plus the distorted grid will make the voltage across the load pure sine. So that is what this load voltage is, scaled down load voltage. And the difference between the distorted grid and the pure sine, this is what you would see. Winding 3, this is across here. Winding 4, this is the difference between the distorted and the pure sine. So these two, when added up, will give a pure sine here. So the grid voltage and the load voltage. Operation of the flux rate switch. So let us say up to this point you had the grid voltage, then this was the voltage the series compensator was making up for the difference to make the load sine. At this point, grid went off. Now this is taking up the full load because flux rate switch has operated and removed this arm out of the picture, and the whole winding is coming across this series compensator, which is now acting as the single and only source and providing the sine wave, so sine wave voltage to the load. Observe here that here there was no grid. The complete load was supplied by the series compensator, voltage controlled inverter. And then at this point, when the grid came into picture, this switch, flux rate switch, opened out, and then the grid is pumping power through winding W3, and the difference power to make up for the distortion in the grid voltage is pumped through W4, and then this is going back again to series compensator mode like a stabilizer. So this would be UPS mode, and this would be the stabilizer mode. Now shunt compensation effect you can see by having this current controlled inverter. So without the shunt compensation, you would see that this is the grid voltage, and then this is the grid current, and there is active and reactive component by the lagging power factor. Now once the shunt compensation is enabled, you will see that the reactive part is taken over by the shunt compensator, and automatically the grid from the grid you will draw only unity power factor. So you see that this integrated magnetic circuit can be a very nice contribution to the sub-microgrid system. I could have many sources, current control sources here, current control sources here, coming from different renewable energy resources, feeding to the loads which are connected here across, and this could be the grid port. So this could be one unit, and then there can be many units. You see sinks, source, bidirectional units, and many such units can be integrated to form an extensible sub-micro network, something like power internet.